Don't look into the wood vortex. Don't. No, turn away, turn away. Hello, Internet. My name is Quinn, and this is Blondihacks. And this is my video for Toolroom Takeover 2025. A bunch of us, I think 12 YouTubers, got together and decided we're all going to make gifts for each other. And I drew Uri Tuchman's name, who I was so excited to get because I absolutely love his stuff. He's so talented, he's so whimsical, he's so creative, and I really wanted to try and make something that would kind of overlap with his style and my style. I make steam engines, he makes really fun, whimsical things. What's the funnest and most whimsical steam engine you can make? I think it's got to be an Aeolipile. These things are ridiculous and a lot of fun and a little bit silly, and I think you're going to love it, so let's go. Here's the version of the Aeolipile that I'm going to try to build. This is my interpretation of a desktop toy kind of version. This isn't the full Heroes engine that you've probably seen pictures of. We need to be able to ship this for the Toolroom Takeover. So I'm going to build this little copper desktop version. This is generally considered the first steam engine, although I think that's literally true, but not technically true, if that makes sense, because steam engine generally means reciprocating or turbine-based, and this is actually a reaction engine. So I think it's more correct to call it the first reaction engine that happens to use steam as a propellant. This invention is generally credited to the Greek-Egyptian mathematician and engineer Hero of Alexandria, but actually it was cited earlier by the Greek philosopher Vitruvius, so he's perhaps the actual inventor of this. And I'm going to pretend that I just knew all that and wasn't just reading you Wikipedia. I dug through my copper bin and I found this piece of 1.5-inch copper tubing and some smaller diameter stuff that I think will make good jets. So let's give this a whirl. Stuff's too big for my tubing cutter, so I'm going to use an old school fabricator's trick. You wrap a piece of paper around the tube, and if the edges of the paper are lined up nicely, then you'll get a nice square cut line. I honestly don't know what are good dimensions for all of the various aspects of this engine. Just because a 5-year-old can look at something and tell you how it works, doesn't mean that thing is easy to build. This is the type of thing where the devil is typically in the details as far as what the exact volume of steam inside should be, how much water it should contain, how big of a torch do you need, how long should the arms be, how big should the jets be, and so on. So I am absolutely winging this. I don't have the right education to know if this is going to work, and I'm just going to find out. Tubing is generally hilariously out of round, and this one is no exception. And I do need it to be fairly round so that I can put boiler heads on the ends of it. So for this reason, I'm taking a bunch of measurements around the inside, trying to deduce an average of what the ID of this tubing is supposed to be. I'm sanity checking also with some OD measurements, and finally I want to know the material thickness, and for that I have this little tiny micrometer with a hemispherical anvil on the bottom, so it can be used to measure thickness on an interior curved surface like this. I'm going to need to make that round and do some other jobs that are all going to require a mandrel, so I've got this nice chunk of aluminum. I'm going to lop a hunk of it off, and I'm going to take it over to the lathe and set it up for some mandrel cutting. This mandrel is actually going to do multiple jobs, so let's go through this. I'll, of course, face off the end, as is tradition. And then I'm going to turn down the OD of this aluminum to what I think the ID of that pipe is supposed to be. It appears to be a 1.5-inch nominal Schedule M municipal water pipe. And so, of course, you can look up what the dimensions of that should be, but I'm going with what I measured just to be safe. This is what I have, not what I think it should be. I'm calling this thing that I'm building a boiler, and again, literally true, maybe not technically true, literally in that it does in fact boil water, but it's not necessarily a pressure vessel exactly. It is, there's some pressure in it, but it's not containing pressure in the way that a traditional steam boiler is for a traditional steam engine. So it needs to hold some pressure, but not a ton. So that's why I think Schedule M municipal pipe is going to be just fine for this. So I cut a delineating shoulder on the back, which will make more sense later, and I put a generous chamfer on the front, which will make more sense in a second, and now I can Yahtzee this thing off. That mandrel's first job is to make the pipe round, and to do that I need to anneal it first. Annealing yellow metals consists of heating them up to a glowing reddish-orange heat, and then letting them cool down naturally. I like to do this with the lights off because it's easier to see the color of the metal then, and you don't risk overheating it because the color of the metal is not competing with your shop lights. Here you can see the nice glowy orangish red that the metal should have. Once you're there, you are done. Let it cool down, and now that metal will be soft like butter. Copper anneals really beautifully. It's just like working clay when you're done that process. So now I'll be able to shove this aluminum bullet down through there with a little percussive persuasion, and that will mostly make this thing round when we're done. I say mostly because it's never a perfect process. The metal doesn't always stretch to conform to the mandrel. Sometimes an egg-shaped area will just stretch out further and still remain egg-shaped, but it will mostly make it round, and then you can tune it up a little bit with some hammer forming around that mandrel to fix up any little areas that didn't cooperate. In principle, you would do this process all the way down the pipe, but little Boilermaker's trick for you, if the ends are round, the whole thing looks round. I don't actually care if the middle is round because it's not going to be attached to anything or enclosed in anything, so I just try to make the ends look round so the boiler heads will fit nice and the whole thing will look cylindrical. Let's get started with the heads now. I've got this piece of copper plate from a previous boiler build. I think it'll be a nice size to get these heads out of. I'm leaving a generous amount of material all the way around. At this point, the dimension doesn't actually matter because we're going to be fine-tuning it later. A good old bandsaw with a 24 TPI blade on it makes short work of these sheet metal cuts. And then these square plates also get annealed because I'm going to be roll forming the heads. Hammer forming would also work great, but since they're round, we can do roll forming, and roll forming is really cool and fun, and I like any excuse to do it. I'll mark the approximate center of both of those, give that a punch, and I'm going to trace with my scribing dividers a circle onto each. The diameter of this circle doesn't matter at this stage. I'm just trying to pick the largest circle that will fit on both pieces. We're going to make it round, but then we're going to tune the final dimensions as we go along to get the right flange to go inside the boiler shell. I need a hole through the center of these for fixturing and for bushings. I'll do this on my trusty float lock vise, which is capable of hanging onto weirdly shaped things because I should have drilled these holes while they were still square and I didn't think of it, so shut up, that's why. I'll drill these holes with my trusty step drill. Step drills are really great for cutting sheet metal because they don't create the lifting forces that a traditional twist drill does, and they create rounder holes in thin materials than twist drills do. Twist drills have a tendency to create three-lobed holes, which is no good. The only downside to a step drill is that you need a lot of space below the work for them to work, hence my block of wood there. I'll deburr those holes now, and we'll be ready to go over to the lathe. Of course, I've rough cut them to shape on the bandsaw, but we're going to want to make them nice and round on the lathe, and the bandsaw saved us a whole bunch of work on that regard. Now, our trusty mandrel comes back because it's going to do job number 2, which is to roll form the heads. I'll get this dialed in so it's running concentrically, and we can start modifying this to become our roll forming mandrel for the heads. I'm going to need a thread in the end of this for fixturing. That's what the holes in the center of the heads is for initially. That's going to allow me to bolt them in place on the roll forming mandrel. The fixturing for this has to be repeatable and easily disassembled and reassembled because we're going to be taking the pieces on and off of the mandrel quite often, as you'll see during this process. Now I can turn this down a little bit. It needs to be smaller by twice the thickness of the head material than the interior diameter of the shell is, so that when we make the flanges on the heads, they will slide inside the tubing. Next, I want to put a radius on that outside corner so that the resulting heads that we form are going to have a nice radius, which in this case is mainly for appearance, but you don't want any sharp corners on a pressure vessel either, because of course that can concentrate stress and create potential failure points. Now, the pressure in this particular boiler is going to be very low. I expect less than 10 psi, so probably doesn't matter. For rounding this corner, you could get out various specialty tools and so on, but honestly, for aluminum and a small radius like this, just filing to a radius gauge is quick and easy. In comes the blanks now for the heads. You can see how these are going to bolt on there, and I've got copper washers to protect the material from the bolt head because I want this to be really good and tight. I've got one central bolt holding all of this against all of the forces, so it needs to be tight. I'm going to start by turning it round. The exact diameter of this doesn't really matter very much. I just want to turn it down to what looks like roughly a good amount of material to bend around backwards to form the flange. You have to have enough. You don't want it to be too short, of course, but you don't want it to be too long either, because the longer this flange is, the more work it is to form it. When we bend that material around this mandrel, we're doing what sheet metal workers call shrinking it. We're forcing that material into a smaller space. The less of that we can make it do, the better. Here's my roll forming tool. It's literally a rollerblade bearing stuck on my tool post, and all we need to do is apply it to the material at an angle that's somewhere between where it currently is and where we want it to be. Just put a little bit of pressure on that, let it roll around a couple of times, and stop. I know it doesn't look like much happened there, but the key to this process is you have to do it a little bit at a time because that copper work hardens almost instantly. So back over to the hearth, and I've re-annealed it, and now we can do another pass. And this is the process, just going a little bit at a time. You can feel on the tool post with that roller when the copper has work hardened and it's not moving anymore. Then you take it off and go re-anneal it. I'll edit out all the annealing for you because it's tedious, but just know that periodically I'm taking it back to the hearth, re-annealing it, and coming back in and doing a little more rolling. And after the first pass, the piece realigns itself on the mandrel, so you don't need any kind of alignment jig or fixture to keep it in the same position each time that you take it off. Once again, the secret to this process is patience. Don't try to do too much at once. You'll just make that roller bearing dig into the work and scratch it up really badly, and you're not going to move it. That copper has to be soft for this to work. At this point, it looks like we're done. However, that head will not fit inside the tube. And that's because when we shrink that metal back to form that flange, it gets thicker. All of that metal is being forced into a smaller space and it has to go somewhere. So it does that by getting thicker. So what we need to do now is turn down that flange to remove all of that excess material that's now piled up there. And it can be significant. In this case, because the piece is a small diameter and we're forcing it into quite a small radius, it actually doubles in thickness. So I'm turning about 35 thousandths off of this to make it fit inside the boiler shell. And there we are. That's a really nice push slip kind of fit. That is beautiful. You don't want it to be too tight so that the silver solder can get in there, but you don't want it to be too loose, of course, because silver solder is very bad at filling gaps. And then I'll square up the back of it with a grooving tool because that roll forming process makes a kind of wavy, wonky edge on the back. And this is the time to trim it down to the right depth of flange that we want as well. We're going to all of this trouble because silver solder joints need a flange, not just for the additional surface area, but silver solder is strong in shear, but not in tension. So the flange turns every joint into a shear joint. There it is. There's one rolled boiler head. On to the next one. The upper flange needs that hole enlarged. So to do this, I'm going to go to the mill where I've got this little block of wood that I rough cut to fit inside. I'm going to put more wood underneath that to get it up off of the fixture plate. And the reason for that is because I'm going to come in here with a step drill. And like I said, step drills need a lot of space underneath them to get down to the depth required on the diameter. I centered that up with a gauge pin, which is sufficient precision for this. It's just a boiler head after all. And in we go with the step bit. You'll notice I've got a piece of shim stock underneath the wood there as well. This depth was going to be close on the step drill, and to make sure I don't drill into my fixture plate, a piece of spring steel shim stock underneath will prevent that because you are not going to be able to drill through that stuff and you'll feel it when the drill touches it. What's left behind is a portal into a wood shop. Don't stare directly into that vortex or you'll get sucked into a space where all the tools around you are screaming banshees of dust and death. So remember, never stare into the woodshop vortex. Stop, don't look at it. Next, we need some boiler bushings to attach things to the top and bottom. So I've got some bronze for that. Bronze is traditionally used for boiler bushings because it doesn't suffer from dezinkification like brass can. Doesn't matter for things that aren't physically attached to the boiler, but these will be silver soldered on, so we want them to be bronze. These are a shouldered bushing that fits into those holes that we've drilled in the heads. And the top one is extra large diameter so that I can drill and tap a hole all the way through it for a fill plug. Much like the flanges on a head, boiler bushings give you a shear joint and also give you material thickness to add threads or whatever other attachment points you need on a boiler shell. I drilled and tapped that 1/2-20, scientifically determined because I have a funnel that will fit in that and I have a plug that will thread into that. And Yahtzee. At the bottom end of the boiler, I need another little bushing that is going to hold the stand. It's going to be the thing that ties this whole contraption together. It also has a shoulder that goes into the boiler shell for surface area, and because it centralizes it on the shell that we rolled. And Yahtzee! I did a second operation on this one, flipping it around in the collet chuck to drill and tap for the little stand to go in. The critical diameter was the outer one, and I like to keep that on the outer end of the work if I can, so that it's easy to test fit the mating part. But it does require an extra setup then. So there's the two boiler bushings mocked up in the heads, and that is the entire boiler assembly ready for silver soldering. So let's go. Silver soldering requires spotlessness, so I'll start with a little mechanical cleaning of the heads, and then everything goes into the pickling acid. This is Asparix number 2, Jeweler's Pickling Acid. Excellent prep for silver soldering. Then everything comes out and gets fluxed and assembled, and I'm going to be silver soldering from the back so that I guarantee nice joints. I'll be able to see the solder flow all the way through the joint and form a nice fillet on the other side. I like to pre-position the solder like this whenever possible because it makes it really easy to know exactly when the joint is the correct temperature, because the solder is already sitting there and it will flow when it's ready to. The other head was done the same way. These are simple, easy joints, and they came out great. That's a really nice looking fillet all the way around there. Next, the shell was pickled and fluxed, and I can assemble the boiler ends for silver soldering. I'm using a lower heat range of silver solder so that I don't damage the existing joints, because I am working very close to them. For these joints, the interface is really too thin for little pieces of silver solder to sit there without falling off, so I'm instead heating the joint up and touching the solder to it when it looks like it's the correct temperature. It's always a little bit messier and harder to execute, which is why I've got some slobbered solder around the edge there, but we'll deal with that in a minute. Check out this sweet, sweet Leidenfrost effect. Gives you a sense of how hot these parts really are. Silver soldering is a very high temperature process, and that sphere of water will dance around on there for a long time. The other boiler head was done the same way. The shell is long enough that I could do the two ends without worrying about damaging the joint at the other end that I've just done. They're far enough apart. And those joints also look really good. Very happy with that. Well, time for the two scariest words in the English language to a Boilermaker: hydrostatic test. Yeah, let's find out if all of our hard work actually resulted in a valid pressure vessel. To do this, we fill it all the way up with water. We don't want any air in the system, only water. And then we attach some sort of contraption. In this case, I made up a little manifold with a pressure gauge and a water input on it. Ideally, you want a check valve on the input to the boiler, but because this is going to be a pretty low pressure test, I think the check valve in my pump will be sufficient. Traditionally, boilers are tested to 2 times working pressure. I'm going to go to 25 psi, which is, I think, 2.5 times the 10 psi that I expect to be in this. The only reason it builds pressure at all is because the steam can be built a little bit faster than it comes out of the jets, but otherwise it's just boiling water. This has to be said every time I do a hydrostatic test. Do not do this with compressed air. That is exceptionally dangerous. I always have commenters tell me, oh, just put compressed air in it and put soapy water around it. No, don't do that. That's fine for a couple of psi if you want to check a fuel tank for water tightness, or a motorcycle gas tank, something like that. People do that all the time. Water tightness is not the same as pressure tightness. If you are using any more than 1 or 2 psi, it is exceptionally dangerous to do that with compressed air. Air is a spring and it stores energy. If any of your joints are not perfect, that will explode and seriously hurt you. We do this with water because water does not compress. We can build pressure, and if a joint on this fails catastrophically, the worst that happens is the first 3 rows get wet, and that is it. It is perfectly safe to do this. So do not do this with compressed air, please. As I do this, you'll see the pressure is bleeding down quite quickly, and that's because my hydrostatic testing setup here is pretty janky. The pump is leaking, and I'm relying on the check valve in the pump to hold pressure, which it's not really very good at. But it's enough that I can test. Because this is such a simple boiler and such low pressure, just kind of pumping it up to 25 psi and checking for leaks is sufficient. But in a proper boiler, like a locomotive boiler, for example, you're going to pump that up to 200 psi, and it's expected to hold that pressure without bleeding down for 20 minutes. And in that case, you have to get all the leaks out of your test apparatus. You got to make sure nothing is bleeding down in any valves anywhere. You got to have a proper input check valve on the boiler. All that stuff has to be right. If you want to see that process done properly, check out one of my other boiler builds in my playlists where I do it properly. This is a janky little thing that's not really a pressure vessel, and this is just an abundance of caution, so I'm whacking it up to 25 psi and making sure it doesn't leak. And that is bone dry, passed with flying colors. Very happy about that, so let's move on and make the little jets that go at the top to create the reaction force that's going to spin this thing. I've got this piece of copper tubing, which is actually salvaged from an old fridge. I'm very excited to find a new use for it. Everybody loves a good upcycle, and those are going to get attached thusly. I made these little baby boiler bushings to give myself some surface area to mount those on the boiler shell. Again, you can't silver solder thin material to thin material. It's just never going to make a good joint. You need some surface area there. So I'll drill out 2 holes across from each other on the boiler, simply drilling straight through all the way to create those. And those are going to be a nice close fit on those little boiler bushings. Now, because there's a joint between the tubing and the bushing and the boiler, they're tiny joints and they're really close together. I decided to do them all at once. So I pickled and fluxed all of these pieces together, and I'm touching solder in there on both surfaces. And that seems to have worked well. A little bit of cleanup, and that should be it for this over soldering work. I'm pretty pleased with how that's going so far. Now, it needs something to spin on, so I dug through my drawer and found this old rollerblade bearing. So I measured up and turned down a quick little brass stand for this. I have no idea what the correct height for this is, just something to get it up off the bench and allow you to get a heat source under it, I guess. I decided to turn a narrow diameter in the middle, both to get some weight out of it so that the reaction engine doesn't have as much work to do, and also because it looks nice. The bottom end gets turned down to be a nice close fit in that bearing. And Yahtzee. The top end gets a thread that will screw into the boiler bushing on the bottom of the boiler. There's a lot of B words in this episode. I hope my pop filter is working. I'm pretty pleased with that little stand. It looks nice, should do the part. It's not too heavy, but still sturdy enough to hold up the container full of water. And look at that, it spins. It's a little bit wobbly, but we'll address that in a minute. And well, let's get some water in this thing and give it a real test. This is a temporary plug I found that'll thread into that top, and let's put some heat on it and see what it does. And what it does is make a giant mess. It's certainly spraying hot water everywhere. You can see it kind of trying to start turning, but mostly it's just spitting out steam at me and spraying a 5-foot radius of my shop with hot water. So I've made a hot water sprinkler, but not exactly an Aeolipile. I applied my many years of high school physics to this problem and decided what it needs is more exit velocity on the gas. So maybe some nozzles will do the trick. On a jet nozzle, the most critical dimension is the orifice diameter. I determined that scientifically by it was the smallest drill I had that didn't require getting out the PCB drills, because I don't know where they are right now. There we go. That's a nozzle, right? I mean, how hard could it be to design a nozzle? The idea of that fridge tubing happened to be the perfect pre-drill diameter for a 1032 thread, so that's what I made those nozzles. I wanted to thread these in and not solder them because I don't know if they're going to work, so it would be nice to take them out and be able to change them, and I don't want to do more silver soldering on this and risk damaging the other joints on the boiler. But threading them seems to work just fine, and let's give it another test. Here comes the torch. Let's see what happens. It will spit some water, of course, initially. I've waterproofed the bench a little better this time. But once we start getting some steam, then we might see some action. Okay, the fill plug is leaking. We'll worry about that in a minute. Come on, it's thinking about it. Oh, yep. Come on, it's thinking about it. A little more heat. There it goes. Look at that. Look at that. It's an Aeolipile. Aeolipile. That's a hard word to say. I don't know how to pronounce it. Man, look at it go. I'm being very careful with the heat because I don't want to run it dry. If you're wondering how come the joints don't melt since that's the same torch I just used to melt those joints earlier, it's because of the water inside. Fun fact, water is the only thing that keeps boilers from exploding. And now some standard Imperial Celebration. I really didn't know if this was going to work, so I was genuinely extremely stoked that it did. A quick note on that water thing, because it is critical to know with all boilers, the #1 safety rule is do not run them dry. If you look at a locomotive boiler, it's got a coal fire in there surrounded by copper or steel, and that coal fire is burning white hot, easily hot enough to melt all of the metal around it. So why doesn't it? Because of the water in the boiler. Water can absorb so much heat, and the water is what's keeping the coal from melting the steel. The primary cause of boiler explosions is the boiler runs dry, there's no more water to absorb all of that heat, and the heat melts the joints and even the steel and copper itself and causes the structure to fail while there's still steam pressure in it, and it explodes. That could potentially happen here as well, so I want to make sure not to leave that torch on there too long and run it dry. Next up, let's make this thing a nice base to sit on. Wood would look really nice, I considered that, but I need something that can hold that bearing really firmly and be waterproof because it's going to get very wet, as you saw. So I found this nice piece of aluminum, put a nice chamfer on it because of course chamfers are what separate us from the animals, and then drilled and bored a nice close fit for the bearing. I've decided I will Loctite the stand into the center of the bearing, and it'll be a slip fit on the base so that you can still take it apart for storage and transport. Now it's still got a lot of wobble in it, and that's because that bearing is more worn out than I think I was hoping, so I'm going to get a new bearing for that. Next, I need a nicer and more effective fill plug. So back over to some brass bar stock. I've put a thread on that, turned it down a little bit, and I'm going to put a knurl on that. This knurling tool was built from a kit by D. Gray Drafting and Design. Go ahead and check him out if you like. It's a really nice kit. It's among the best of the knurling tools I've tried. Knurling tools are never great, but this one actually works better than most. But of course, the real secret to a good-looking knurl is to chamfer both sides of it. Like makeup and lighting, it can make anyone look pretty darn good. There's also a groove at the base of that thread, and I put a counterbore in the top of the boiler bushing so that an O-ring can seat down in there and hopefully seal that up nicely with just fingered pressure on that. So it won't spray all of the pressure that we're building out the fill plug like it was earlier. Now for finishing, I thought about this a long time and I kind of went back and forth on it. Traditionally in model engineering, what we would do is paint this black with high temperature paint, partly because painting it hides all the sins. It's almost impossible to make all perfect looking silver solder joints. Maybe if you're better at it than I am, you can, but I've yet to see any boiler that doesn't have a little bit of solder dribbled here and there. It's pretty hard to avoid, and you can't completely file all of it off because it gets bonded so closely to the surface that you can't remove it without removing too much copper. Now everybody's going to say, oh, you should polish it and make it look all nice. Yes, that's a nice thing to do in principle, but the thing that YouTube never tells you about yellow metals is that they tarnish extremely fast. So you can polish it up and make it look beautiful for a YouTube thumbnail, but then in a week it's going to be tarnished again. And I've never found any kind of clear coat or anything that prevents that. If you find such a thing, every boat owner in the world would like to know about it. However, I also don't necessarily want to paint it because standard operation involves pointing fire at it, and I'm not sure if any high temperature paint can necessarily stand up to direct application of a torch flame. It's not really what it's designed for. So I think I am going to polish it effectively, as best I can anyway. I can't, like I said, make all of the little solder blobs disappear, but shine it up as best I can and make it look nice for the YouTube thumbnail, and then it's going to be tarnished by the time it gets shipped. It's also going to need cleaning after this one final test run that I'm going to do just to see it all come together. Wait, hold on. Mail's here. Got a little package from Erik, who you might know as Engineer Raised in Kingston. He's a fellow YouTuber, and he drew my name for this little experimental gift exchange. So let's see what he has gone and made for me. I honestly have no idea what this might be, but it's extremely well packaged, I will say that. I suppose a better YouTuber would have mic'd themselves for the authentic reaction to come, but I'll boost the volume so you can hear me. Whoa, this is amazing. That was 100% authentic reaction. I was absolutely floored by this thing. I didn't know what to expect. I thought maybe some sort of tool or fixture, jig, something like that. I was not expecting a model engineering style perfect scale model of my shop, including all the little lathe tools. It's all a combination of machining, laser cutting, 3D printing. Everything is incredibly tiny and incredibly well made. There's even a little sprocket, a little shop cat to keep me company. He included an extra box of chamfers as well. That's always nice. Good to have those around. So I'll store those for later. You can never have too many chamfers. Now, I know what you're wondering. Does the lathe actually work? Of course it does. Look at this. Carriage hand wheel. That moves nicely. A little cross-feed hand wheel. The tailstock works. The little chuck spins. It's really, really amazing. Little tool holders slide in like that. Little Loris tool post. Now, there's a power outlet on the side, so there's more. He warned me I was going to need a 12-volt wall wart. I didn't have one, but I did find this barrel jack in my electronics bin and hook that up with my bench supply. There's a little control box here that he made that plugs in there. Little cat on that. Ace. Now, gotta turn on the breaker, which is, of course, in the breaker box. Now, let's see what happens here when we give it some juice. Does it chooch? Oh, signs of life. There it goes. Yep, it chooches. Look at that. Look at that little chuck. This is pretty fantastic. Hello, Internet. My name is Quinn, and this is Blondihacks. Who's that idiot? Do I sound like that? I'm a moron. I mean, I have to find out if this thing can make chips. Let's try a little facing cut. And you can't really see it on camera, but there is some very fine brass powder coming off of this thing, so it is in fact making chips. I'll see if I can do a turning. And yeah, rigidity obviously a bit of an issue. It's struggling to do a cut there. Oh, now the tool's come loose. Well, it does make chips though. The facing cut did kind of sort of work. He's machined a perfect copy of the prismatic ways on my lathe. Look at that. There's so much machine work in that. And look at the cross slide. There's actually T-slots and dovetails machined into it. Machining those kinds of form features at this small size is very difficult. That's really beautifully done. Four-jaw chuck is functional. He says it is possible to dial it in, although it's, quote, an experience. But the machine work on this chuck is incredible. To make functioning jaws at that size, really, really something. Wow, thank you, Erik. I'm totally speechless at this. This is amazing. Make sure to check the links below if you want to see Erik's video on how he made this, and also a link to Uri opening the Aeolipile that I made for him. Well, I hope you enjoyed watching me make this Aeolipile. Drawings are available on my Patreon if you want to give this a whirl. Thank you for watching. Thanks to my patrons for making all this happen, and I'll see you next time.